Okay, in this video, we're going to finish off Newton's laws and talk about Newton's third law, and then go into what applications this can provide us. Okay, so most everybody knows Newton's third law from like an elementary school saying that says every action has an equal and opposite reaction. Okay, that is the essential phrase we always hear from Newton's third law. And what it essentially means is that if I have an object, or two objects rather, and this is important, you need to have two objects. So in this case, object A and object B. Okay, Newton's third law has nothing to do with what's going on outside the contact of these two objects. In other words, if I have a force here, say F1, and a force here, F2, those two forces have nothing to do with the third law interaction between the two boxes. Okay, third law occurs right here in where the contact is being made. So they're mostly internal forces to the system. Okay, and that's the important part there. They are internal to the system. Okay, whereas these yellow forces that I drew represent external forces. Okay, and Newton's law doesn't apply to the external parts. They only apply to the internal. Okay, so let's focus in on this. So you've got these two objects touching. Let's zoom in on the picture, right? So you had object A, and over here we have object B. And we want to focus in on the interaction forces between these two objects. So what you're going to see from this is that if, say, you were object A, you would feel object B pushing on you with some amount of force. But if you were object B, you would feel A pushing on you also with a force. And so the question is, how do these forces compare? Now, the way that the forces are usually written out is you would typically write it with the force and then two subscript labels. Okay, and so the way this translates is that this is the force on B due to A. Okay, that's how that's read. Okay, and it follows that Newton's second law tells us that if I set this up and I see that there's a force on B coming from A, there's also a force on A coming from B. Okay, and as Newton's law tells us, these forces must be equal and opposite. So they're equal in magnitudes but opposite in directions, and we can see that from the picture. Yellow force points to the right, green force points to the left. Okay, and again, so when we see these internal forces, the other thing that is important to note about them is that all internal forces cancel each other. Okay, and they cancel each other because of Newton's third law. They are equal and they are opposite, and so since they're both applying to each other, they have no effects on each other. Okay, okay. So here's where the applications of Newton's law becomes a big deal. Okay, if I have these two objects A and B and I put them next to each other, they are pushing on each other, but neither of them move. Now, is that because the internal forces are canceling? And the answer is no. They're not moving because externally there is a friction that's applying in both directions on each individual object, and so that's why they don't move. But what if you put something out, say in outer space? Okay, how does Newton's third law work there? Well, if I've got two objects, okay, so again, say object A, and we'll say this object has a mass of 10 kilograms, and I put it next to another object, say whatever, so just something different. Okay, and it's bigger. In fact, we'll say it's about 10 times bigger. It's with a mass of 100 kilograms. Okay, these two objects, because they're touching, are going to have Newton's third law interaction forces on them. Okay, at the point where they meet. One pushes on the green, and green pushes on the yellow. And again, these forces are equal and opposite. But if we were watching this happen in space, which object is going to move more? Okay, so the forces are the same. Okay, so the force on yellow from green and the force on green from yellow. Okay, so these forces are equal and opposite. All right, and in order to understand which one's going to move further, so recall Newton's second law, mass times acceleration is generally the net force. Okay, so if I was the green object, the only force acting on me is coming from yellow. And so that means this would be equal to the mass of green times its acceleration, because it's the only force acting on green. If you were the yellow object, it would be your mass times your acceleration. Okay, now a visual representation, because the masses are so different, that kind of helps understand which object moves, is when you look at the masses. Yellow's mass is much larger than green's mass. Okay, but since the products are the same, right? Since these products are the same force, the same magnitude of force, what do I have to put in for the accelerations in order for this to balance out? Well, if one has a much larger mass, then it will have a much smaller acceleration. Whereas the green mass is very small, so it needs a very large acceleration to balance out that force. So the end result would be that you would see yellow move a little bit away from green at a small speed, whereas green would move away from yellow with a much larger speed because it has a much greater acceleration. Okay, and so that's the idea of Newton's third law, is that the objects move differently because of the masses, but the forces between them are always the same. Okay, one of the examples they give in typical questions is what would happen if you had, say, let's just imagine like a baseball bat. Okay, so this represents a baseball bat, and then you had a ball coming into the bat. Okay, so we know that the ball is going to hit the bat, but the bat's going to also hit the ball. Okay, so the question is, well, which one applies more force? Now we know that after it hits, the ball is going to fly off with a great velocity. But the bat doesn't really go anywhere. In fact, the bat still moves through the ball, but let's just say the bat has no change in velocity. Okay, does that mean the bat applied more force on the ball, or did the ball apply more force on the bat? And remember, it's always true that when the two objects are interacting, their forces must be equal and opposite to each other. And that is always, always, always true, no matter how the question asks it. Okay, you could have a car towing a truck, a truck towing a car, and so the truck is applying a force on the car, and the car is applying a force on the truck, and those forces are going to be equal. It doesn't matter if the system is moving at constant speed. It doesn't matter if the system is accelerating. It doesn't matter what the system is doing. If the two objects are interacting, their forces between them are equal and opposite, no matter what. Okay, another good example for that would be to think of the Earth. Okay, so if we were to look at, say, the Earth, okay, and then you are standing on the surface of the Earth. Okay, if you were to jump in the air, so say someone right next to you jumps in the air, right? All right, we know that gravity is a force that's going to pull you back down. Okay, but it also follows that because of Newton's third law, you also apply a force upwards on the Earth of the exact same amount. Okay, so if you jump in the air, you fall back down to the Earth, but while you're in the air, you are tugging, well, really always, but you are tugging on the Earth with the same amount of force that the Earth is tugging on you. But why is it that you move towards the Earth and the Earth doesn't move towards you? And the answer comes back to that idea that these forces are equal and opposite. However, for the mass of the Earth is huge compared to the mass of the person. Which means, in order to balance this out, the acceleration of the Earth is really tiny, but the acceleration of the person is really big. So you actually fall towards the Earth, but the Earth doesn't move towards you, at least not noticeably. There is a very small acceleration, but it's so incredibly tiny that you will never perceive how this would work. Okay? In fact, we did an experiment in one of my other classes where if we said that the average mass of every human being was 70 kilograms, okay, and we know there are 7 billion people on the planet, if we put all of them in one spot and had all of them jump at the same time, then the force of Earth is, or the gravitational force from Earth is going to tug all 7 billion people down at once. Okay? And when that happens, that means that all those people are going to tug up on the Earth. And so we looked at, well, what would be the acceleration of Earth if that happened? Okay? And I don't remember the exact number that we came up with, but it was something like 8 times 10 to the negative 14 meters per second squared. Okay, it was a very, very, very tiny amount of acceleration. And to give you an idea of what that acceleration would do, we said, well, how long would it take to move the Earth? So to move the Earth 1 centimeter towards us. So 0.01 meter. Okay, and so think about that. Look at a ruler and look at 1 centimeter. Okay, it's not a very large distance. And what we found was it would take almost 6 days for the Earth to actually move 1 centimeter. Okay, and that's because that even though there's 7 billion people at 70 kilograms, which comes out to like 4.9 trillion kilograms of mass, that is nothing compared to the mass of the Earth, which is about 6 times 10 to the 24th kilograms. Okay, the mass of the Earth is still huge compared to all 7 billion people on the planet. Okay, and so even then, if we jumped, we would have to be in the air, not touching, because once we're touching, all the general movement between us is canceled. But if we were still in the air falling towards the Earth, we would have to fall for exactly, or almost 6 days in order for the Earth to move 1 centimeter towards us. Okay, but that's why we don't see it happen, but it doesn't mean it's not there. So again, the important thing with Newton's third law, forces are always equal and opposite when they're interacting with other objects. Okay, you also have to think of it as it's two objects with two forces. Here's what I mean by that. Let's say we have this box on the surface. Now, if we make a free body diagram, and it's just sitting here. So let's say there's no friction, no applied forces. The box is just sitting on a surface. We know that there's gravity pulling it down and a normal force pulling it up. Now, since it's not moving, we would say that the normal force is equal to the gravity because the net force is 0. What's important to understand is that this is not a third law interaction. Okay, and the reason why is because these are two forces acting on one object. Okay, and Newton's third law requires us to say two objects and two forces, right? Think about it. We wrote that the equation was force on A due to B is the negative force of B on A, right? We needed two objects. We needed object A and object B. We need to know the force of A on B and the force of B on A. It changes the perspective. First, your object A, and you feel the force from B. then your object B, and you feel the force from A. That is a third law interaction. In this case of just being this box, you're feeling gravity pull you down and the normal force pushing back up. That is not third law interaction. Okay, what would make it third law is you feel a normal force from the surface, okay, but the surface feels a force pushing down on it. That's what suddenly makes it third law. Okay, is that if you're put it this way, you're touching the surface, so the surface is pushing up on you. The ground is touching your surface, so it has a normal force pushing back on it. And those two are what make it a third law interaction, not the two forces that are just acting on the box. Okay, and so that's very important. Okay, so one of the applications we get to when it comes to Newton's third law is the ideas of pulleys. Okay, because when you have a pulley, so it's pulleys and rope. Okay, the idea is that when you have an object, like let's say two objects are attached by a rope, okay, and something's moving them, right? So say it's like, instead of, these are masses, this just represents a group of people, and it's tug of war. So each one is trying to pull the box pull the rope in opposite directions. Okay, so what does that mean about the tension? Well, you would feel tension if you're on the left here. You would feel tension towards the right, and if you were on the right, you would feel tension towards the left. Okay, now since this is one single piece of rope, the force of tension is an internal force. Okay, and because of that internal force, those two forces do not have any effect on the two objects' movement whatsoever, because internal forces cancel to the system. Now the external forces, so that's the ones that are here in yellow, these forces, being external, are what's going to cause the system to move. Okay, and so that's the idea of dealing with when you have rope attached to two objects. Now if, on the other hand, we throw a pulley in there, okay, so the typical example of a pulley is what we call an Atwood machine. Okay, and so an Atwood machine would look something like this. You have a table, you put a box on the table, call this one A, and that box is attached to a pulley, which then has another box hanging below it. Okay, and what happens is that as box B falls, box A is going to move. Okay, and so it's considered a system because they're linked together by this rope. Now, one of the important things that you're not going to understand quite now, but you will when we get to that unit, is that the pulley has to be massless and frictionless. Okay, it's frictionless if it rotates freely on its axle, and massless just because once a pulley has mass, it then has a resistance to how it wants to turn. And we're going to get more into that when we cover rotations. But for right now, consider it massless and frictionless, which means that when this box, when B wants to fall downwards, that's because gravity's pulling it down. And so therefore the rope applies a tension upwards. Now on box A, okay, there could be other forces acting on it, but for right now, we'll say there isn't. And all it feels is a tension force trying to pull it to the right. But again, you'll notice these tension forces are facing towards each other. Okay, and all the pulley does is changes the direction of the force. Okay. Now, of course, there's more to pulleys than that, and if you took physical science in like middle school or wherever you took it, they cover something in simple machines where pulleys have a mechanical advantage, and the more pulleys you have, the more it helps with your output work versus your input work. But we're not going to focus on all that right now. For right now, the pulley just simply changes the direction of the force. So what we can do then is ignore the pulley was there and look at the system a different way. Okay, because right now, you'll notice that since there's two objects, we'd have to make two free body diagrams. So you have the diagram for box B, which would be its gravity and a tension force. And then you'd also have a diagram on A. Okay, and so on A, you have tension to the right, its gravity downward, and it's on a surface, so it has a normal force. Now, if we were to try and solve the system for, say, what's the acceleration, okay, the way to do that is you'd have to solve for tension in one diagram and then plug that in for tension in the other diagram. And it's not a hard process, but it's a lot easier if you see the whole thing as one big system. So here's how we're going to do that. So imagine you have box A. There's no friction, so let's ignore the surface for right now. Okay, it's attached by a rope directly to box B. Because remember, all the pulley did was change the direction of the force. So if I remove the pulley, right, so if I took that pulley out, it's almost like we could take box B and put it so that it's straight out from A. Okay, and that's what we're doing right now. We're making it so it looks like it's straight out from A. Now, don't let this change anything about the applied forces. The force of gravity on B is still trying to pull the system over. So I'm going to say that force due to gravity from B is trying to pull the whole system. Now, of course, we said there were tensions here in the rope. But since those tensions are internal to the system, okay, they're going to cancel each other out anyways. We could write this as this is just one big combined object because these internal forces cancel, and this whole system is being tugged by a force due to gravity acting on B. So now if we apply Newton's second law to this, F net equals ma, the net force, the only force acting on it, is the gravity from B, so that's mb times gravity. And then when we look at the ma part, well, how much mass is this system tugging on? And the answer is, well, it's tugging on both masses combined. And that's causing the system to have an acceleration. So if I want to solve this for acceleration and I divide over the masses, we simply get mb times g all over the sum total of the masses. Okay, and that is a much quicker and easier way to solve the problem if we look at it in terms of systems. Okay, let's look at another example. Another popular example would be to have the same idea, box A. Okay, and box A is attached to a pulley, and then that's attached to a different box, say box B, and we'll say box B is significantly bigger, so we know that this system is going to fall on the side of box B. Box B is going to fall downward, and box A is going to move upwards. Okay, so what would be the acceleration of this system? Well, again, it's a system. So ignoring, if we first draw our forces that are acting on this whole thing, we have tension tugging up on B, gravity tugging down on B, there's a gravity tugging down on A, and a tension pulling up on A. Well, if we do the same trick, where we imagine these objects going side by side, right, connected by a rope, okay, then we can look at it in terms of the system instead of an individual box in a box. You've got gravity from B to the right, you have gravity from A to the left, okay, and then you have these internal tensions. But again, forces internal to the system cancel each other. So this is really box A and box B attached to one another, so it's really one big object that is being tugged on in both directions by a gravity from B and a gravity from A. So if we look at the net force Newton's second law. Okay, what is the net force that we would write? Well, we'd have gravity of B tugging to the right, and then gravity of A to the left, so those forces would be a difference. How much mass are we tugging on? It would be the sum total of both masses. So there's the red one and a blue one. So if I wanted to solve this for A, we would divide off the masses. And so let's put in the gravity for B. Okay, so the gravity on B would be a mass times gravity. The gravity on A would be a mass times gravity as well. Keep in mind, these masses are different. That's why I'm trying to keep them in color code. And then we would divide that by the sum total of the two masses. And that would be our acceleration. Okay, and again, you could solve this problem by not turning the system and just doing two free body diagrams. But remember, that would mean you have to solve for tension in one and plug it into the other, and the algebra gets a little messy. Okay, and we're going to focus on more strategies on free body diagrams and making your net force equations in class. So I'll do an example with how you would solve for the tension and substitute it in class, and prove to you that doing it from the system standpoint makes it a lot easier and a lot more conceptually sound than the mathematical way we're going to do in class.